Hello everyone, welcome back. Today we are going to see stereochemistry, and the most important, we are going to recap the multiple choice questions and objective questions of stereochemistry. So let's begin. So this is what we are going to see in this video, that is MCQ, true or false, and match the pair. All these question types are common in all competitive exams, and practicing can boost your confidence and accuracy. So let us begin with the first question. It is enantiotropic ligands are distinguished in which type of environment? So the option given are achiral environment, chiral environment, both chiral and achiral environment, and D, none of these. So the correct option is chiral environment. Basically children, enantiotropic ligands are those ligands which are identical ligands in a molecule, and that can exchange position through rotation or flipping, but exist in enantiomeric environment, that is in a chiral environment. So the key characteristics of enantiotropic ligands are chemically identical but spatial arrangement is different. Enantiomeric relationships are important in this. Okay, so basically enantiotropic ligands are equivalent. You should remember this. Then next is, which of the following is an example of a molecule with enantiotropic ligands? So the option given are 1,2-dibromoethane, 1,2-dichloropropane, 2,2-dimethylpropane, and benzene. So if you see, the first question was enantiotropic ligand. So here they have given the example also. So in the example we have to find out which molecule will have same uh, ligands or identical ligands in the given example. So in the given example, if you go through it, you will find that first and second carbon has dichloro, and if you write the structure, there will be 2 chlorine and 2 hydrogens on first and second carbon, so which are identical, but you will find that these molecules, if you exchange the positions, they are going to have spatial arrangement difference. That's the reason why answer B is the correct answer, that is 1,2-dichloropropane. Okay, then the third one is diastereotopic ligands differ in which of the properties? So diastereotopic, again children, you try to study the definitions of all these diastereotopic ligands, then enantiotopic ligands, so that you can solve such type of questions. So if you see diastereotopic ligands, they are chemically reactive, then they interact with the chiral environment, as well as the NMR chemical shift also they will show. So all these properties are there for diastereotopic ligand. That's why the option D is correct, that is all of the above. Now next one is, in hydroxylation of trans-2-butene using cold dilute KMnO4, the product is dash. So here what we are doing, we are trying to do oxidation, that is hydroxylation of trans-2-butene. Now while we were studying our question answers, we have already done this question. So you always get a racemic mixture. Okay, when trans-butene, because it is stereoselective. This is an example of stereoselective reaction where trans-2-butene will always give you racemic mixture. Okay, so the option A is the correct option, that is racemic mixture of RR23 butadiol and SS23 butane diol. And cis gives us always, yes, student, do you remember was the what will cis butene give? Cis butene is going to give you only one product, that is meso product. Now the next is, yeah, the same. See, just now we were discussing. The next question is again on the cis butene. So hydroxylation of cis butene using cold KMnO4 gives. So as I mentioned before, that a meso 2,3 butane diol we are going to get using cis-butene. Again, this is again a stereoselective reaction. Next is, which reagent is used for epoxidation of alkenes? Now, the options given are osmium tetroxide, peracid, that is MCPBA. So it is metachloro perbenzoic acid, KMnO4, and H2PD, that is your catalytic reduction catalyst. So here for epoxidation of alkenes, as you remember in the theory part, we have seen that peracids are used. So the correct option is B. Now next question is, epoxidation of trans-2-butene using peracids gives dash. So epoxidation of trans will always give, basically epoxidation gives you, epoxidation is going to give you the epoxide, but here they are trying to find out, because it is trans-butene, so you have to give the correct option, whether it is meso, whether it is racemic mixture, whether it will be trans, whether it will be cis, all these things. So in the theory part we have seen that the epoxidation of trans-2-butene gives us a racemic mixture of epoxide where it is trans-butane with epoxide ring. That means the CH3 groups will be opposite side of the epoxide ring. Okay, which is the expected product of bromination for trans-2-butene using bromine? So for trans-2-butene, if you are going to have bromination reaction, what is the correct option? So obviously in the previous slide also we have seen that trans-butene, if it undergoes bromination, it is going to give you racemic mixture of enantiomers. Okay, so the correct option is B. Next, which of the following is true about the prochiral center? Now basically if you know the definition of prochiral center, you can answer this question. So prochiral center, they can be converted into chiral center by changing one ligand. Okay, so the correct option is B. Prochiral center, what is the definition? That center which can be converted into chiral center by changing one ligand. Okay, so option B is correct. Now in next one, in bromination of alkene, the reaction follows dash. So whenever there is a bromination of alkene, it follows a anti-addition. Okay, so here the option B is correct. Now next is, the topocity of the ligand is determined based on dash. Again you should know the definition of topocity. Topicity is, the behavior is in the chiral environment is topocity, basically you are going to see the chiral environment of the molecule. So these ligands will try to behave in the chiral environment. So option B is correct. The next one is, stereospecific reaction gives dash, a specific stereochemical outcome. So stereospecific reactions will always give us specific stereochemical outcomes. Okay, that means trans will give, if trans is giving us cis or cis is giving us trans, those are called as stereospecific reactions. Then in which of the following reaction does stereochemistry play a key role? So the options given here are epoxidation of alkenes, hydrogenation of alkenes, hydrobromination of and oxidation. So which of these reactions is going to play the important role because of stereochemistry? Now if you see all these reactions, epoxidation of alkenes, hydrogenation of alkene, then hydrobromination, all are going to have a very important role of stereochemistry in these reactions. So the option D is correct. Addition of bromine to 2-butene is dash. So addition of bromine to 2-butene, obviously we have seen previously the first second slide we saw bromination of 2-butene both for cis as well as trans. So we have seen that the cis butene always gives us meso product and trans butene gives the racemic mixture. So here it is giving a stereoselective reaction also and stereospecific. So the option C is correct, because addition of bromine to 2-butene will give you both stereoselective also and stereospecific reaction, means product. That's the reason why option C is correct. Now 15th one is when an optical alcohol is treated with, okay, when it is treated with, let me highlight this so that which question we are reading you can just concentrate on it. When an optical alcohol is treated with thionyl chloride, the OH is replaced by chlorine. So this, read the question properly. It is alcohol treated with thionyl chloride. Okay, so you have gone through this in the theory part. So whenever the alcohol is treated with thionyl chloride, it is SNIA mechanism, because you are going to get the retention of the configuration, not inversion of the configuration. If you get inversion of the configuration, then it is SN2, but we are using thionyl chloride. That's the reason why it will be SNI mechanism. Okay, and we will be getting a retention of configuration. So the correct option is C, that is we are going to get retention of configuration. Next one is when two ligands of molecules are replaced by zinc Z atom one at a time, give a pair of enantiomer. So here Z can be any atom where you are going to replace one of the ligand by Z one at a time, and if we get a pair of enantiomer, then such ligands we know that it is called as enantiotopic ligands, because we are getting pair of enantiomers. So the ligands will be known as what? Enantiotopic ligands. So option C is correct option. Now the next one is minus. Minus here indicates levorotatory. Okay, 17th one, see the 17th one, it is minus 2 bromo-octane. So minus indicates levorotatory. So 2 bromo-octane is treated with dilute NaOH, only plus 2 octanol is obtained. So here the reaction which is taking place where bromine is replaced by OH group. So it is a SN2 reaction, and you will find that minus has been converted into plus, means levorotatory has been converted into dextrorotatory. So whenever there is change in the isomers, enantiomers are formed. So obviously the reaction is enantioselective. Plus has become minus or minus has become plus, so it is enantioselective reaction. Because enantiomers are formed selectively, we are getting one enantiomer. That is using levorotatory we are getting dextrorotatory. So the enantiomer we are getting, that's the reason why such reactions are called as enantioselective reactions. Okay, they are known as enantioselective reactions. Now let us go to the next one. So let us start now the next, that is true or false. The first one, enantiotopic ligands are chemically identical but exist in enantiomeric environment. So obviously this is true, because we have seen that enantiotopic ligands are chemically identical but they exist in a different environment, that is chiral environment. So it is true. Next is diastereotopic ligands give the same signal, NMR signal, in both achiral as well as chiral environment. So this is false. It will not give the same NMR signals, but it will show different signals due to diastereomeric relation. Okay, so here the answer is false. Then next is a racemic mixture has an enantiomeric excess of 0%. So it is a racemic mixture. So obviously the enantiomeric excess cannot be there. So this is true. The statement is true. Then the next one is homotopic ligands in a molecule become diastereotopic in a chiral environment. So the statement is false, because homotopic means same. Homo is same ligands. They remain equivalent in all the environment. Okay, please try to understand. There are heterotopic ligands and homotopic ligands. Now homotopic means if a carbon is having for example hydrogen, so all the hydrogens will be same. Okay, they are same or they are equivalent, and in all environment they will remain as equivalent ligands only. That's the reason why the answer is false here. Okay, the statement given is false because the homotopic ligands remain equivalent in all the environment, whereas they have given the statement as homotopic ligand in the molecule become diastereotopic in chiral environment. No, they cannot become diastereotopic. Okay, then next is a prochiral center in an sp3 hybridized carbon with two identical substituent that can be converted into chiral center by replacing one of them. So this is true because when you, the definition itself tell you that a prochiral center can be converted into chiral center by just substituting at least one of the atom. So if you replace one of the atom, two identical atoms by different atom, then you will be getting a chiral center. So this is the definition of prochiral center. So it is true. Next one is hydroxylation of alkene using cold dilute ChemONotes in a stereospecific and occurs via syn addition. So the hydroxylation takes place by syn addition. This is correct for alkenes. So it is a true statement. Now next, all tetrahedral carbons are prochiral. So it is false. All tetrahedral carbon cannot be prochiral because the condition for prochiral center is at least two groups should be identical. Okay, minimum two groups should be. Only those carbon which have two groups identical can be prochiral centers. If there are three groups which are identical, then we cannot have the prochiral center. Correct? So the statement is false. Now the next is bromination of 2-butene occurs via syn addition mechanism. So this statement is false. We have seen already. It goes via trans addition or anti addition. Okay. So bromination of 2-butene goes via which addition? It goes by anti addition. So this statement is false. Next one is epoxidation of cis-2-butene with per acid gives you meso epoxide. So here cis gives meso product that we know. So this statement is true. Okay, epoxidation of cis-butene is going to give us epoxide using per acid. So you will be getting a meso epoxide. Then the next one is epoxidation of trans-butene gives a single optical active product. That is false because we don't get single trans-butene gives us racemic mixture. So the meaning is racemic mixture means you will be getting both plus as well as minus product, means enantiomers we will be getting, which will be 50-50%. That's the reason why we call it as racemic mixture. So you will be having both the enantiomers using trans-butene. So the epoxide which will be formed will be a racemic mixture of the epoxide. That's the reason why this statement is false. So let us go to the next objective type of question which is asked in the exams. Those are match the pair. So based on these topics which we have discussed today, that is prochiral center, stereospecific reaction, stereoselective reaction, heterotopic, homotopic. So the match the pair are also based on these topics only, okay, of stereochemistry. So stereoselectivity you can see in column A, then SNI reaction, stereospecificity, prochiral carbon, SN2 reaction, hydroxylation of ChemONotes, SN1 reaction, epoxidation of cis-2-butene with per acid, and the ninth one is they have shown heterotopic phases and homotopic ligands. So here the options are given, we just have to find out the correct option. Okay, so you can just pause the slide and video and just try to find the correct answers of each one. Now I can give you 2 seconds and try to find out stereoselectivity, what will be the answer, then prochiral carbon, what are the answers. Okay, so you can have 2 minutes and then we can go to the answer. Now student, let us see the answers. The first one is stereoselectivity. So the option for this is, the correct answer is, only one out of the two stereoisomers will be formed during the reaction. So the word itself tells you that stereoselective means we are going to select the one isomer out of the given stereoisomers. Okay, so if one isomer we get in the product during the reaction, so such reactions we call it as stereoselective. Then the next one is SNI reaction. SNI, we already seen that using thionyl chloride, when the reaction proceeds, we always get a retention of configuration. Okay, so the correct option here is retention of configuration. Then the next is enantiomeric excess. So the enantiomeric excess, the word excess says that it is more, excess in quantity. So what is excess in common quantity? The enantiomer. So out of the two enantiomer, if one enantiomer you get it as the product or is in excess, then we will call such reactions as EE reactions or enantiomeric excess reaction. Then the fourth one is prochiral carbon. So we have already seen the definition of prochiral carbon, the carbon which has two identical atoms and which can be converted into chiral, which can convert the molecule into chiral carbon. Okay, so if the center, that is carbon center, can be converted into chiral by just replacing one of the atom which are identical by substituting that group, only if one atom is substituted and if we are going to get a chiral carbon, then such carbon atoms we call it as prochiral atoms. Then next is SN2 reaction. So children, we know that SN2 is substitution second order reaction. So this SN2 substitution reaction proceeds by one step process. So when you must be in 12th standard, you must be remembering SN2 reaction as second order reaction but undergoes by one step process. Now the next one is hydroxylation using KMNO4. So hydroxylation using KMNO4 reaction is stereospecific because the KMNO4 reaction, when hydroxylation takes place, it is going to get added from one side, that is syn addition. That's the reason why we will be getting stereospecific reaction. Okay, so this is syn addition. Next one is SN1 reaction. So it is nucleophilic substitution first order reaction. So nucleophilic substitution first order reaction means it is going to undergo by two step. So the correct option is two step, that is G. Next one is epoxidation of cis-2-butene with peracid. Epoxidation of cis-2-butene with peracid. So the correct option here is it forms a meso-epoxide. We have seen during fill in the blanks or true or false that epoxidation of cis-butene will always give us meso-epoxide. Okay. Then next is heterotopic phase. So heterotopic phase are those carbon atoms which have, or the phases which are ligands which have two non-identical phases of the molecule. Okay, not identical. Hetero means different. So here the correct option is two non-identical phases of the molecule. Then the last one is homotopic ligands. So in homotopic ligand, the word itself tells us that homo means same. So equivalent in all the environment, including the chiral ones. Okay, such ligands are called as homotopic ligands. That is same environment which are having. So that's all for today. We have seen the stereochemistry based on few topics like enantiotopic ligands, diastereotopic ligands, prochiral centers, what is topocity, then what are heterotopic, homotopic, and few reactions we saw. Now the same thing, whatever today we have seen the objective types of question, its question answers video is also uploaded. Just go and watch those videos so that you can understand the theory part also of stereochemistry. Okay, this is stereochemistry part 2 because we are going to consider not the basic stereochemistry, that is enantiomers, diastereomers, that is the basic one which comes under stereochemistry 1. Okay, So whatever we are watching, that is stereochemistry part 2. So thank you for watching, and you can excel your examination. Be a good student, keep learning, happy learning. Thank you, and please like and subscribe the channel. Thank you, student.